All right. So, as I said, we're basically dealing with here today all about traveling in space. And well, one of the things we do in space is we have orbits. And a satellite is an object or body that revolves around another body due to that gravitational attraction we talked about, that universal gravitation, the F big G. So there is two types of satellites. There's an artificial satellite is a satellite that is man-made. Other satellites would be like the moon. The moon is a satellite, so it's obviously a natural satellite. Now, a set of well-known artificial satellites is the network of 24 satellites that make up the Global Positioning System, GPS. Using 3 satellites, the intersection of the 3 circles will actually give you the location of an object to within 15 meters of its location. So this is how they find out things. Now, this process is called triangulation. So if you ever, I guess you guys don't have your license, but if you're driven with anybody in a car and they have a GPS and you're following it along, and sometimes you come to an intersection and it tells you to turn like 10 meters later than it should, it's because the GPS is only good up to about 15 meters. That's its extent. Now, again, there is many, many more satellites in Earth than 24. There's I don't even know, probably hundreds, at least hundreds, maybe even thousands. And it's becoming a bit of an issue. It wasn't an issue initially because there wasn't that many up there. And the problem is some of the older ones, there was no escape plan. And so there's no way to get rid of the satellite. It's just floating up there. And I know what somebody might ask is, can we blow it up? Well, if you blow something up in space, all the pieces stay in space and they're traveling at a very high rate of speed. And so if you blew up one satellite, you're essentially having a million bullets traveling in space that will never stop. So that it's a bit of an issue now. And so what happens is that when companies now put a satellite in space, say like for a cell phone company or a weather company or whatever that company might be, their satellite needs now by law, universal law, or I guess global law now, is it needs to have an escape plan. How do you get out? Now, getting back into orbits and how we get things to orbit is that for any object in an orbit, you have a force of gravity or force of attraction. So this actually should be F big G. And to stay in perfect circular motion, that force of gravity, force of gravitational attraction, must be equal to our force of centripetal force that we looked at in our last unit. So those two have to be equal in an effort for your object to remain in orbit, to doing a perfectly circular orbit. Now, that means in terms of our formulas, our F, again, this should be a big G here, our two formulas have to be equal, where our force of universal gravitation has to equal our force of centripetal force. And so if I make these two equations equal, I can actually do a little bit of math here. And the mass of the satellite I can cross off, which is on both sides. The distance between the middle of each mass, the Earth and the satellite, that can be, we got 2r squared, which is r times r in the bottom here, and r in the bottom here. And since there's 2 in the bottom here and 1 here, you can cross one of them out each. And so essentially, we can rearrange this formula and figure out what velocity your object would need so that you could be in a perfect orbit around the Earth or around any large mass, right? So that's that big M, the large mass. That is the M, that's the mass that you are orbiting. And again, the radius is the distance between those two masses. Now, again, talking about orbits and satellites. So you need an exit plan. And one of those things that they have now as an exit plan is they have a booster rocket at the end. And so what happens is if your velocity becomes too great, your centripetal force required to keep that object in orbit is greater than that force of gravity, which doesn't change. But if the velocity changes, then your centripetal force that you need becomes greater. And so what happens is if you increase the velocity, the object flies off into space. And so again, this is what a lot of satellites have, is if they die, they don't work no more, they have a booster rocket that increases the velocity dramatically, and then the object flies into space and we never see it again, and so it doesn't bother us. The other thing that they've considered doing, but it can be a bit of a problem, is having booster rockets the other way, where you slow down the object. And so if the V becomes too small, now your centripetal force is less than the force of gravity. And so what happens is the object will spiral into the atmosphere or ground. Now, what happens is usually our atmosphere takes care of business and it absolutely destroys mostly everything, burns it up. But there is going to be some junk that, is going to make it to the Earth's surface, but not too much, It'd just be a little couple rocks here and there, a couple pieces of metal. Now, here's also what we're entered. So we know the velocity it takes to orbit a large mass or any mass. Generally, it's a large mass we're talking about here. Now, the other thing is what we're interested in is the period of orbit. How long does it take to complete that orbit? And so here's an equation that we're going to use. Velocity equals d over t, very standard. Velocity equals distance over time. But for us, the distance we're talking about is an orbit. That's the circumference of a circle. In other words, going all the way around the Earth. The time that would take is called the period of revolution. And so what we can do is, rearrange this formula so that we can find t, the period of revolution, is equal to 2 pi, the radius, divided by the velocity. And so I'm going to come back to this and show you how we can determine how long it takes for something to travel around the Earth or travel around the moon or travel around the sun, perhaps. All right, so let's get to example 1 here. Whoa. Boom, right here, there we go. So we're going to determine the speeds of Venus and Earth as they orbit the sun. Venus has an orbital radius of 1.0 times 10 to the 11th meters, while Earth, which is farther away from the sun, has an orbital radius of 1.49 times 10 to the power of 11 meters. The mass of the sun is very, very big, 1.99 times 10 to the power of 30 kilograms. All right, so we're going to do, what are we going to do first? Let's go with Venus first. All right, now, whoops. Come on, computer. Oh, nothing worse than the blue circle. No, don't do this. Come on, man. All right, give it a second here. Love technology. Well, that one's working. Oh, no, it's not. Oh, man. All right, we're back in action. All right, so again, here's the formula I'm going to use. As long as I can. I'm going to try to go out of pen here. Come on, man. Not responding again. That's a first. All right, here we go. All right, hopefully we're back. So again, we're looking at the velocity of our planets. Now again, this is a formula I just went through. The velocity needed to orbit a planet is g, that big constant we have, the mass of the object that you're orbiting. Nice way of saying the sun here. Okay, that's what we're orbiting here. All right, divided by the radius, the distance between the centers. Okay, so the first one, like I said, we'll check out Venus, see how fast it's traveling around the Earth, around the sun, sorry. All right, so again, looking for the velocity. V is equal to, again, I'm going to take the square root. All right, now G value is 6.67 times 10. This is our constant, gravitational constant it's called. Negative 11. Again, we won't get into units because it's crazy. There's lots of different crazy units there. But our velocity, again, because we're in standard units, is going to be meters per second. All right, so the mass of our sun here, again, big M is the object that we're orbiting. So Venus orbits the sun. We all do. All the planets do. All right, so there we go. Now it says the orbital radius of Venus is 1.08 times 10 to the power of 11. All right, so again, a little bit of a math lesson here. All right, because you can't do this all in one step, but again, I'm going to show you, for those of you who are struggling with scientific notation, we'll get at her here. So on the top here, again, I'm going to multiply my numbers. All right, so I'm going to take that 6.67, and I'm going to times it by 1.99. And I'm going to get 13.27. All right, again, times 10, going to use my exponent rule here. 10 to the power of negative 11 times 10 to the power of negative 30. Keep the base the same. Add the exponent. It's going to be power 19 there. All right, now down on the bottom, nothing changes. So we still got this 1.08 times 10 to the 11. All right, now that could further be down, is that I can divide my numbers. So I'm going to take that 13.27. I'm going to divide it by the 1.08, and I get 12. Two decimal places here, 29. All right, now again, using my power rules, I got 10 to the power of 10 to the power of 19 divided by 10 to the power of 11. So again, keep the base the same. This time I'm subtracting the exponents. So 19 minus 11 is 8. All right, so what I'm going to do now is just type that number into the calculator and take the square root of it. So here we go. So 12.29 times 10 to the power of 8. There we go. Get a big number there. Take the square root of that number. Oh, man, I typed it in. Whoa. There we go. And so I'm getting, here's my numbers. After I did that, I typed in the calculator. This is how fast Venus is moving. 35,014.28. Not like the 28 matters, but again, going to two decimal places. And we're in standard units here, meters per second. That is how fast the planet is traveling around the sun. All right, now, next up, I'm going to do Earth. All right, so I'm going to use the same formula here. All right, so I got V equals, again, big square root symbol here. I got my G value, which is, again, that 6.67 times 10 to the power of negative 11. Now I'm going to be able to skip a step here. I'm going to show you why, but I got the mass of the Earth. We got 1.99 times 10 to the power, times 10. Throw that in there. Power of 30. That's the sun. The only thing that's different here, right, is our orbital radius, because Earth, we're a little bit farther out here. It's 1.49? Whoops. Back it up here a bit. 1.49 times 10 to the power of 11. There we go. Now, listen, here's why I'm telling you I can skip a step is the calculations on the top are the same. I still have that 6.67 times 10 to the negative 11 and times that 1.99 times 10 to the 30, and this is what I got, 13.27. So I don't have to redo that. It's the same calculation because we still have the gravitational constant and we're still circling the sun. So that's going to be to the 19th. All right, and then down here again is the 1.49. Times 10 to the 11. All right, so let's see here. I figure that out. So again, take the square root of, I'm going to divide those two numbers. So I'm going to take 13.27, and I'm going to divide it by the 1.49. And I get 8.991, rounded two decimal places, times 10, again, using my exponent rules. 19 minus 11 is an 8. And so the velocity of Earth, this is how fast we're traveling. I'm going to take that 8.91 times 10 to the power of 8. All right, then I take the square root of that number, and this is how fast Earth is traveling. We're doing this right now as we speak. We don't even know it though, right? To 29,000. Oh, we're going so much slower. 849.62 meters per second. All right, so we're going slower than Venus. Venus is going faster than us. Well, we're still moving. All right, now, so there's how fast we're going. All right, so now I get to that. That number is going to be key. We're going to need that 240. Here, I'm going to write that down because we're going to need this. 29,849, because this is an interesting thing coming up here. We'll get to that last formula that I looked at. Find the amount of time required for Earth to make one complete revolution around the sun. All right? So this comes back to the formula I had with the period. How long does it take to go around the sun? 2 pi r, all right, divided by v. Now, the orbital radius I gave you. We just figured out the velocity. So I'm going to substitute those values in. So let's see here. I got 2 times pi, and then our radius there, that was given, right? That was the 1.49 times 10 to the power of 11. All right, now we just figured out the velocity there. And that velocity was, I just wrote it down, 29,849.62. All right, now, again, I'm going to do this, all the numbers. I'm going to go 2 times pi, which again is 3.14, times a 1.49. See what I get here. So let's see here. I go 2 times, because there's something interesting coming up here that a lot of people don't realize. 3.14 times 1.49. And here's what I'm getting. 9.36. And again, I don't have any other exponents, so it's times 10 to the power of 11. And I'm going to divide that by 29,849.62. All right, and let's see here. So my t-value is going to equal, so I'm just going to type this into my calculator. So I got 9.36, or I got 357, same thing, times 10 to the power of 11. Let's see, there it is, divided by 29,849.62. And here's my number. Whoops. Oh, no, I messed it up. Okay, got to go again. Here, 9.36 times 10 to the power of 11. There we go. Divided by 29,849. I want to make sure I do this right. It's very important. There we go. Okay, so here's the answer I'm getting. This is how long it takes for the Earth to go around the sun. 3,135,7,183.11. Now here's the thing, we're in standard units. This isn't seconds. So that's how many seconds it takes us to go around the sun. I'm going to do a little something here. I'm going to, first of all, that's seconds. So I'm going to divide that by 60. That's in minutes. So now I got 5,226, 19.71. That's minutes. I'm now going to divide that by 60. Because now I'm getting it in hours. 8710.33 hours. I am now going to divide that by 24 to get it into days. And I get 362.93 days is my actual answer. Now, the real answer, because I did a lot of rounding, let's be serious, right? I did a lot of rounding. And here's what the real answer is. That's why I say it's interesting. The real answer is 365.256 days. But we always say that there's 365 days in a year. That's not true. The true definition of a year is it actually takes 365.25 days. And so what happens is, because we are shrinking a year by a quarter of a day, every year we go along, we're a quarter of a day off. And so after 4 years, we're 1 day off. And that's why we have February 29th, a leap day, every 4 years, is to account for this calculation. Now, over the thousands of years, this little thing here, this 6.6, it's going to be a factor. We're going to be ahead. And so in maybe 1,000 years, there's going to have to be 1 year where they have to do some accounting and have maybe a February 30th, not just a 29th, but you're also going to have a 30th to get us back on track. But a year is actually on Earth is 365.25 days. And again, that's why we have a leap year, because we get a quarter ahead every year. And then after 4 years, we have a leap year, and that gets us back to square one, where we're actually on time again, where our calendar makes sense and our seasons make sense. Not like they do in Canada anyways. It seems like we have 4 months of winter, 4 months of summer, and a month of spring.